Okay, we're going to be beginning Unit 5, which is Systems of Equations. And 5.1 is going to introduce exactly what systems of equations are and how we're going to solve them graphically. So let's begin with this example here. Jules opens a checking account with $500 and plans to spend $50 each week. Astrid opened a checking account with $50 and plans to save $25 each week. An equation showing the relationship between X, the number of weeks, and Y, the account balance, is shown for each account below. Graph each equation and use the graph to answer A through C. So, essentially they're wanting us to graph Jules' equation and Astrid's and compare them. So, Jules began with $50 but spent, $500 and spent $50 each week. So let's start over here on the graph. X-axis is weeks and Y-axis is the balance. So Jules began with $500 and then is spending $50. So this account is going down $50 each week. So if you look at the scaling here, you'll notice that it's changing every line by 50s. So we're going to go down 50, and then the x-axis is changing by ones. So down 50, right 1. And then we're going to continue that pattern, and then we're going to get a straight edge here. We're going to do our best to create a straight line all the way through the coordinate plane. Okay? And actually, there's not an arrow on the end here because that was a beginning point. And there's actually an end point because once you run out of money, you cannot keep spending that money. Okay, next, we're going to look at Astrid's account. And Astrid begins at $50. And Astrid is saving $25 each week. So for Astrid, we're going to start on the y-axis at 50. And Astrid is gaining $25 per week. So you can say he rises 25 and runs 1. Or you can double that and say he gets $50 every 2 weeks. Okay, that's your preference and how you want to plot that. So we are going to draw our linear function here. Now Astrid's, if he continues with that pattern, it begins with $50, but his will continue to rise unless he stops saving the money. So let's go answer the questions. A is asking, where do the graphed lines intersect? So right here you see there is a common point where they intersect, and this point is actually at 6, 200. Okay, so we're going to go ahead and put that over here. The intersection is 6, 200. Okay, all right, so now they're asking us, what does that point of the intersection represent in context to the situation? So they're saying, okay, these people have some money, they're saving and spending. What does the 6 actually represent? And what does the 200 represent? So the 6 is the X value. So that is going to be weeks. So you would say after 6 weeks. Now the 200 is the Y value, which represents the balance. Both will have $200. Okay, so after 6 weeks, both Jules and Astrid will have $200 in their account. All right, C says, prove that point of intersection is a solution to each equation by substituting the values into the equations. So we're going to prove it. So let's take Jules. Jules is y equals negative 50x plus 50. But instead of y, we're going to substitute the 200. So we have 200 equals negative 50. And instead of x, we're going to substitute the x value of 6. And then plus, this was 500, plus 500. Okay, so we're going to do this multiplication. Negative 50 plus 6 is negative 300 plus 500. And then negative 300 plus 500 is 200. So that point, 6200, did work for Jules. Let's make sure it is also going to work for Astrid. So y equals 25x plus 50. Instead of y, we will substitute 200 equals 25. But instead of x, I'm going to substitute a 6 for x plus 50. Let's go simplify this. So we have 25 times 6 is 150 plus another 50. And 150 plus 50 is 200. So that same coordinate, 6200, worked for Astrid as well. So we have just proved algebraically that the coordinate 620 satisfies Jules' equation as well as Astrid's equation. Okay, so let's come down here and switch this up and let's look at some of the vocabulary that we're going to have to use. Two or more linear equations that use the same variables forms a system of equations. So a system requires two equations at least, and at least two variables. And those two variables must represent the same thing. So in the example up above, x was weeks and the y was the balance. Okay, the solutions to a system of the linear equation, it is the ordered pair. Again, that's the coordinate. That ordered pair makes all the equations in the system true. Right? So that ordered pair is called the point of intersection. Okay, we're basically asking ourselves, what coordinate do all the equations have in common? All right, so these notes seem like they're very lengthy, but there are lots of graphs that take up a lot of space, but we're going to be able to answer these questions very quickly. So here we have a system because we have two equations. They're both using the x and y axis, and all they're asking for is what is the solution. So remember, it has to be a point on both of these lines. And there is one point that both lines have in common. That is the point of intersection. And this coordinate here is 3, -2. That's it. Where's the point of intersection? That is the solution to the system. All right, next example. You will see we have two lines. So this is a system. What do they have in common? Where is the point of intersection? Well, they only intersect once, so there's only going to be one solution. And the solution is the ordered pair, -1, -1. Okay, again, the third one. We have two linear functions here. They have one point of intersection, so there is one common coordinate that both lines share. That is 2, 2. So the solution to the system is 2, 2. Okay? All right, let's talk about how many solutions you can actually have when you have a system. Now, in Algebra 1, we are just working two equations, but as you advance, you can have many more equations to a system, but we are doing two equations for the meantime. So, the following types of solutions are possible when solving a system of linear equations. All right, so let's look at this example. When you look at the graph, you can clearly see that these two lines only intersect at one point, right? That is going to be your actual solution where they intersect. Okay, so if you look at the two lines, you'll notice one is going up with a positive slope and one is going down with a negative slope. So the lines, when there's one intersection, they will definitely have different slopes. And when they have different slopes, they will intersect at only one point. So if there is one intersection, there's going to be only one solution. So intersecting lines only have one solution. Okay, here our lines are not intersecting. These lines are parallel, and we learned about the slopes of parallel lines in Unit 3. So if they stay parallel and never intersect, they are going to have the same slope. So lines that have the same slope, but they have different y-intercepts. You'll see this one crosses in the negatives. This one crosses above the origin, so this y-intercept is positive. Their slopes are the same, but y-intercepts are different. Do they ever intersect? No. So this one with parallel lines will always be no solution. Okay, this one is a little difficult to see, so I'm going to add a little bit of color in here. Okay, this is still two lines. So I'm going to say, okay, my first line is going to be this little turquoise color. I'm going to make my arrows a little larger so you can see it. Okay, and then the second line is going to be right on top of it. I'll extend it and put my little pink arrows out here. So it's two lines, but they are right on top of each other. Okay? So they're essentially the exact same line, right? They are exact same lines. They're exactly the same. They're just right on top of each other. So these lines have the same slope and they have the same y-intercept because they are exactly the same. So if they are exactly the same, they're going to have a whole bunch of points where they're intersecting. Every single point is an intersection. So we call this infinitely, oh yeah, I think I spelled that right. Okay, actually I think this is an I. Let me fix this. So infinitely, there we go. So infinitely many solutions. All right, so one intersection is one solution, no intersection is no solutions, and lines that are the exact same that are overlapping have infinitely many solutions. All right, so let's look at these examples below. Again, this is very quick because today is all visual, looking at the graphs. So here we have our system. This one crosses one time, and the solution is 2, -1. All right, the next example, we have a system, and it appears like these are parallel, and they are never going to intersect. So this one is no solution. Okay, the third example, they are intersecting once. So they have different slopes, and they're intersecting at 4, -4. Now would be a good time to pause the video and attempt to do these independently, and then come back and play the video to see if you're getting your solutions correct. All right, so this fourth example has one intersection. So there's going to be one solution. The common coordinate they both share is -1, 4. Again, one intersection. This coordinate, 4, -3, is the one coordinate that both lines share, so it is the one solution. Okay, last one. The lines have the same slope, therefore they will never intersect, and if they do not intersect, there will be no solution. So summarize, how do you find the solution of a system of equations? Well, all we look for is we are going to find the point of intersection. Okay, that is which point, or it could be a whole bunch of them, do they have in common? Okay, which points do both linear functions have in common? Okay, all right, so let's go ahead and we're going to sketch examples of each. All right, now this does not have to be specific. It's very general, so we want you to make your own sketches. They don't have to be identical to mine. So first one is one solution. One solution means we are going to take two lines, and when we draw the two lines, they are only going to touch once. So I don't need anything specific. I'm not going to mark specific y-intercepts or specific slopes. All I'm going to do is draw two lines, and these two lines just need to intersect one time. Okay? There are a lot of different possible answers here. So everybody does not have to have the exact same system. Mine happens to intersect at -1, 0. Okay? All right, next one, infinite solutions. Okay, this means that they are the exact same line. They don't touch once. Okay, these will never touch. These touch all the time. All the time. So I'm going to go ahead and draw a linear function. Again, it doesn't matter what it looks like right now. I don't have to get a specific slope or y-intercept. So there's my first linear function. And if it has infinite solutions, kind of turn my paper here, they have to be the exact same line. Right on top of each other. Every single point is exactly the same. Okay? And then my last example says no solutions. So if it's no solutions, they will never intersect. And the only way to make that happen is they have to have the same slope. So this is important that my slopes are the same. So I'm going to start right here, and I'm going to make a +2 slope. So I'm going to rise 2, run 1, and then I'm going to draw this linear function that has a slope of 2. Okay, right there. And then I'm going to draw a second linear function. I do not care where it touches the y-axis, but it has to have the exact same slope. So I'm going to put it down here. And it's still going to rise 2, run 1, rise 2, run 1. This is going to create two lines with the exact same slope, which means they will be parallel. Now there may be some human error in here because we're not perfect at drawing straight lines, but you get the idea. We have two lines with a slope of 2, and they are parallel. They will never touch, so there are no solutions. Okay? All right, so let's go ahead and let's advance this. We're going to incorporate the new skill of locating solutions of a system with our prior knowledge of how to graph from equations, and that does also include isolating y. So first, you must make sure both equations are in slope-intercept form. You have heard these words a million times since junior high, so hopefully you are already aware that means isolate y so that it is in y equals mx plus b. You're then going to graph both equations, and you're going to look for the point of intersection. Okay? Once you find the point of intersection, write your answer as an ordered pair. Okay? You have to write the whole coordinate. We're not solving for x. We are finding a coordinate that both lines have in common. Okay? All right, so let's begin with our first example. I'm going to do the first one in green here. Starts on the y-axis at -4. And it is going to rise 1, run 3. So up 1, right 3, put a new coordinate. If I try to go again, it puts me off the coordinate plane, so I'm going to reverse it, and I'm going to go down and left, keep that pattern of the line going upward. All right, now when you do this, it is very, very important that your lines are straight. So make sure you are using a straight edge, like your ID is a great straight edge. It's straight and it's not too big. It's the perfect size for you to draw your linear function. All right, the next one here I'm going to put in orange. This one is going to start at a +4 on the y-axis. 1, 2, 3, 4. And this one is going down with the negative slope. So down 7, right 3. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3. Looky there. That is where they're actually going to intersect. So we will draw this linear function. There is the point of intersection, which is at the ordered pair 3, -3. Okay? So we are incorporating our graphing skills from Unit 3. And then the new skill is identifying the solution to the system, which is the common point that they share, 3, -3. Okay, all right, let's move on to the next one. I'm going to graph the first one in red. So it's going to begin on the y-axis at a +3. We are going to have a positive slope, so we're going up 1, right 3. Oop, that one takes us off as well, so I'm going to do the reverse. It's going to be down here somewhere. Down 1, left 3. Take your straight edge. We're going to draw the linear function. Remember, the linear function goes to positive and negative infinity both ways. Now we're going to graph the second linear function. This is what makes it a system, more than one. So -2. And then this slope is 2. And remember, that is the same thing as 2/1. So we're going to rise 2, run 1. And we're going to repeat that, rise 2, run 1. And there's that common point. So this one also has one intersection, and the solution is the ordered pair 3, 4. Okay, now your solutions may not always be whole numbers. That's why it's important to draw straight lines. When they end up being decimals, that presents a new problem if you're not using a straight edge to draw your linear function. So be careful with that. All right, so the next one we are going to plot. Let's see. Y equals -7x minus 3. So we'll start at -3. We are going to go down 7 and right 1. 1, 2, that's taking us off the coordinate plane. So instead of down right, I'm going to have to reverse that, correct? Because my line should be going down. I need to go up 7 and left 1. So we will draw this linear function here, connecting these 2 points. Okay, now I'm going to look at the second equation. Oh, the second equation is just y equals 4. So reminder, if you don't see an x, your graph is not going to intersect the x-axis. It is only going to intersect the y-axis. And they're telling you it has to touch the y-axis at 4. So I'm going to go to my y-axis at 4. And then I got to think, how do I draw a line? Do I draw it up? No, that's going to cross the x-axis. Do I draw it down? No, that's going to cross the x-axis. So if it cannot touch the x-axis, it's going to have to be parallel to the x-axis. So we need a horizontal line because the horizontal line will never touch the x-axis. So again, if you look at the first line I drew, it has a y and an x. It is going to touch both the y and the x-axis. If it only has a y, it is only going to intersect the y-axis. Okay, so we again have one point of intersection. So this system has one solution. It is -1, 4. Okay, all right, so let's move on to number 4. This would be a great chance for you to pause the video and to do this one by yourself to make sure you're understanding how to graph and locate the solution to the system. And then you can play it again to see if you're doing it correctly all by yourself. All right, so we're crossing at -2. We're going down 2 because it's negative, and then right 3. So 1, 2, 1, 2, 3. All right, 2 points is all I have to have, especially if you have a straight edge. Okay, we'll take this straight edge, draw this linear function. There we go. And then now we're going to graph the second linear function. The y-intercept is a +4. This one is also going down because it's negative, and it's going down 8, right 3. So 1, 2, 3, 4, 5, 6, 7, 8, and right 3. And there we go. We actually landed right on the point of intersection. So when you draw that linear function, you can clearly see one point of intersection, which is at 3, -4. Now, remember to check these. I could take the 3 value and substitute for x, and -4 and substitute for y, and I should come out with a true statement. And that should be true for both equations. If it does not substitute algebraically and both of them come out true, then you have graphed your linear functions incorrectly. So if you were on a test and you're wanting to make sure you get a very high grade, that is how you would substitute and check to make sure it works out algebraically. Okay, so now we're going to use Desmos to find these solutions. Instead of graphing manually, you are going to open your calculator, whether you use a calculator or Desmos. We're just most familiar with Desmos at this point. And you are going to graph both of these, which you should know how to do, so I'm not going to demo that for you. Okay, after you graph both of them, you're finding the point of intersection. Okay, so I suggest that you pause this video and you go practice your graphing skills, come up with your solutions, and then come back and check them to make sure you're doing them correctly. Okay, so I want to point out on this first example, if you will notice that in the first equation, the slope is negative 2/3. And in the second equation, the slope is also negative 2/3. That means that these are going to be parallel lines. Now, don't just trust me. Go graph those in your calculator and make sure that they're parallel. So if they are parallel, they will never intersect. So these will have no solution. Okay, this system has no solution. Okay, all right, number 6. I notice this slope is negative 6, and this slope is negative 1. So they have different slopes. Okay, they are not identical. So when I go plot these in a calculator, I'm going to notice that there's going to be one intersection. Okay, go test it out. Make sure I'm telling you the truth. That one point of intersection, all you have to do is click on it, is going to be negative 1, 3. Okay, all right. Number 7. This slope is negative 3/4, and the second equation has a slope of 1/2. Again, they have different slopes, so these lines will intersect one time. Okay, so go graph those, take a look for yourself, click exactly where they intersect, and you should see 4, 1. All right, number 8. I notice the slope for the first linear function is 5/2, and then the slope for the second linear function is negative 1. Okay, they are not the same, so they're not parallel. There's no way they're the same line. These, again, different slopes, means there's going to be one intersection. So we go graph those, click on the point of intersection, and you will notice that they intersect at the coordinate 2, 1. Okay, number 9. All right, number 9, they're already telling you what y equals. So in my ordered pair, I actually know that the y value has to be negative 5. It's the x value I'm unsure of. Okay? When I try to go graph 6x plus 8y equals negative 22 in Desmos or any calculator, it is not going to graph it for me. Okay? But what I can do is I can substitute a negative 5 for y and then solve for x. That's one of our options. So I'm going to do 6x plus 8 times, well, instead of y, I'm going to substitute a negative 5 in there, equals negative 22. So 8 times negative 5 turns into 6x minus 40 equals negative 22. We're going to add the 40 to both sides, and you get 6x equals 18. And now we divide both sides by 3, and you get x equals, I'm sorry, I did that wrong. You divide both sides by 6. I jumped ahead and gave y'all the answer by dividing by 3, and you get 3. See, even us teachers make mistakes. We have to catch our own mistakes. So we get the solution, x equals 3. So the coordinate where they intersect is going to be at 3, negative 5. Okay? So again, I could not graph 6x plus 8y equals negative 22 in my calculator. I would have to have solved that before I could do that graphically, which you are allowed to do. Okay, same thing for number 10. Okay, this will not graph this way. That's one of the questions they're asking you down here. What did you notice about 9 and 10? Well, 9 and 10, you could not graph. You could not graph, okay? You just can't graph equations that are set up like that in standard form. So it says, what do you think we need to do to solve them? Okay, well, what do we need to do? We need to put them in slope-intercept form. Okay, again, that means we need to isolate y. So the equation is in y equals mx plus b. Then we can graph manually or use the calculator to graph. There is another option, if you recall. You can also plot x and y intercepts. So if you remember how to do that, that's another way that you could graph this system. It's just personal preference. So right here, I'm going to go ahead and isolate these for y'all. This is a skill we'll be practicing quite a bit. The first equation, when we isolate y, we have to add the 7x over, so it becomes positive. And then we're going to divide the 7 by 2 and divide the 18 by 2. So we end up with 7 over 2x plus 9. Okay. In the second linear function, we subtract the 6x over, so that becomes a negative 6x. We don't need plus 0. And then we're going to have to divide by a positive 6, so we end up with negative 1x. So here are the two equations that you would be graphing in the calculator and finding the solution. So I'm going to leave that up to you to complete that solution. Okay, so good luck today. Hopefully you get a lot of review on graphing linear functions, and finding the common intersecting point is actually going to be pretty easy for you. I just know it. Good luck.